Once we have a quantum dot and we have defined the qubit type of choice, then maybe a first thing that we want to do is to focus, can we also have qubit readout? Because only if we have readout, we can obtain information about the system. And I want to highlight here two popular versions. One is maybe a more historical version, and the other is the workforce of today. And then there are variants thereof. So first of all, energy selective readout, also sometimes called Altman readout. This is a very efficient, elegant, simple way of qubit readout. So how do we do this? Well, we just require there's an energy difference between our two basis states. So for example, the spin down and spin up state of a qubit in the Loss DiVincenzo proposal. So if we have a magnetic field, then these two energy states are split. Then if we have another reservoir, a reference frame to provide to, we can align these two levels such that only one level is above the reference and the other level is below. And what does this mean? Well, it means that the excited state can escape to the reservoir in this case. The spin down state, which is below the reference, cannot escape and is being blocked because it needs to go to an empty space to escape. And so that means that if we have a qubit state and we want to have a readout, that what we can do is that we can align it such that only the spin-up state can escape. If it's doing so, this will provide information on the system because the charge state of the system is changing, and the charge state we can measure very sensitively using charge sensors. This was the starting point of many experiments in the past. Why? We just need one quantum dot and one reservoir. And this reservoir was almost guaranteed to be there, because to get the electrons in the quantum dot, we would need a reservoir. And so this reservoir can then be reused to later on do the readout. It also creates a large signal, at least in relative terms, because a single electron entirely goes away to the reservoir. And so the signal measured by a nearby charge sensor is exactly determined by the coupling of the single electron charge to that sensor. And that entire signal can then be used to infer whether the quantum state was spin up or spin down. There are also some challenges here, maybe in the fabrication already in the design, because this will require that each and every quantum dot that's going to be used for readout will require a nearby reservoir. Now, if you have still in mind this kind of 2D array, why are these reservoirs if we also want to have the quantum dot qubits to be near exchange coupled to one another? From another point of view, it's also the signal that comes out of the system. For example, the tunneling is probabilistic, and one does not exactly know when the electron or hole is going to tunnel out to the reservoir. And since we don't know this, we have to integrate over the time such that we are confident enough that we have a high fidelity readout. One could of course argue, well, just make a very large tunnel coupling such that the electron goes out fast. But if one is doing this, then most likely also another electron will go fast in. And so the total signal will be very small or limited in time. And so our question is then, what is the bandwidth that one has in a readout system to optimize this part, but at least not the entire time over which one is integrating is going to be resulting into a measured signal. So from that perspective, this is not an optimized way of readout, but it's still a very elegant way of doing because it's so simple to include. Perhaps a more appealing manner is actually to reuse a quantum dot nearby quantum dot. So if we have this picture again of a two-dimensional array of quantum dots, one may imagine that one is implementing a certain algorithm, qubit operations. In the end, we want to do a readout. Well, okay, then we can maybe use another quantum dot to read out the state, such that, let's say, every quantum dot used for measurement requires another ancilla for readout. Then one can do what's called Pauli spin blockade readout. And here you see two animations of the system where you can see the difference if we are changing the detuning or the relatively alignment of the energy levels from one quantum dot to the other. And so if we're changing this, then only one electron can escape to the other quantum dot if it's in a certain spin state. This can, for example, be the singlet state, such that only a singlet state is possible, allows for to have two electrons in one quantum dot. And so if the system is in a certain triplet state, either the T minus, T0, or T plus, it will be blocked. And so by using these two quantum dots, we can project it onto a single quantum dot, such that in the end there's a charge difference, in particular for the singlet state in this case. If there's spin-orbit interaction, there may be different possibilities that one has, which states will be blocked and which ones will not. But in general, the argument remains the same, that certain levels are being blocked and certain levels not. Again, if we have this charge sensor in the nearby hood, then it's the coupling of the two quantum dots to that sensor that determine the signal for measurement. For example, if one imagines a linear arrangement, then the closer quantum dot will have a stronger coupling to the reservoir, and that relativeness in the stronger coupling will provide the measurement signal that one can use to discriminate between the two states. So Pauli spin blockade, it only requires two quantum dots, and in particular not a reservoir. Right? Maybe reservoirs are still needed at the edges to load the system, but not for each and every quantum dot used for measurement again. However, we also see advances there, and in particular for latch readout, there's another conversion, because if one is converting from the one state to a double occupied state in a quantum dot, there's a time scale, the relaxation rate of the excited state to the ground state, and this may be limited. And so it makes sense if one can then convert this into kind of a definite charge state. This can be done via what's called latch readout, such that, for example, only the excited state can escape and the ground state is blocked because it doesn't have the energy to escape to the reservoir. This will result in a larger signal and also a longer time stability. Of course, in terms of the scalability, it will require to have a reservoir in nearby hoods. However, one may also envision the scheme to be efficient if one has, for example, three quantum dots, where the third quantum dot is used to create a metastable time state. In general, Pauli spin blockade is rather effective compared to the energy selective readout or ultimate readout. Why? Because the readout starts at time is 0. As soon one is doing the pulse, one can start to differentiate between the two signals, at least at the time scale of the tunnel coupling, because it's not probabilistic. And so it's fast and guaranteed.